So the last section in chapter 2 has to do with recursion. And the warm-up problems all have something in common. Hopefully you were able to get through them and seen what they have in common here. So in the first problem we have a staircase is 12 stairs, and you can take each stair 1 or 2 at a time. And we want to know how many different ways could you go up that staircase, and of course the order matters here. So you see that if you try to just start listing the different ways, for example, you could just take them all 1 at a time, 1 plus 1 plus 1 plus 1, all the way up to 12. That would work. Or you could do something like 2 plus 2 and then a bunch of 1s. Or maybe 2 plus 2 plus 2 plus 2, that's 8, 9, 10, 11, 12. Well, but then you can kind of rearrange these in any order that you want. You could do 2, 1, 1, 2, 2, 1, 1, 1, right? So if you try to list them all, it seems very quickly to be unreasonable to do. And if you're looking at this and thinking that these look like compositions of 12, compositions from the last section, you're right, they are compositions of 12, but thinking about this as a compositions problem is probably not the best way to do it, because all of these compositions are going to have something in common, which is that they won't all have the same number of parts, but they'll all be made up of 1s and 2s. Right? They can only have 1s and 2s, and we don't yet have any nice way of counting the compositions into parts that are restricted in some way like that. So instead of doing this using compositions, what I suggested is that you look at some smaller cases here and see if you can answer this question for a smaller number of stairs, and then look for a pattern. So we're going to look at some smaller staircases, a staircase with just 1 stair or 2 stairs or 3 or 4 or 5, and try to work our way up. And now here we're going to fill in how many ways can you climb a staircase with this many stairs. I'm going to call this number Cn just so I can refer to it later. So if your staircase just has 1 stair, it looks like this, there's only 1 way to climb it. It's to climb that 1 stair, so just 1 way. But if your staircase has 2 stairs, there's now 2 ways to climb it. You can either take the stairs 1 at a time, 1 and 1, or you can take 2 stairs at a time. So there's 2 ways, and I'm going to list them as 1, 1, or just 2. So over here I'm just listing them all. In the first case, there was only 1 way to do it. If your staircase has 3 stairs, this is where it starts to get a little more complicated. You can either take them 1 at a time, 1, 1, 1, or you could take 2 stairs and then the last stair, 2, 1, or 1, 2. So there's 3 ways to take 3 stairs. For 4 stairs, we could either do 1, 1, 1, 1, or we could do 2, 1, 1, 1, 2, 1, 1, 1, 2, or we could do 2 stairs and then another 2 stairs. Right, so there's 5 ways to go up 4 stairs. This is already starting to get a little bit tedious, but I don't necessarily see a pattern here yet. So I'm going to just do one more case and see if that helps me to figure out what the pattern would be. If my staircase has 5 stairs in it, I can either go up them 1 at a time, so 1, 1, 1, 1, 1, or I could do 2, 1, 1, 1, 2, 3, 4, 5, or I could rearrange that and I could do 1, 2, 1, 1, 1, 1, 2, 1, or 1, 1, 1, 2. What else could I do here? I could go up 2, then 1, or 2, 1, 2, or 1, 2, 2. And I think that's it. I think these are my only options here, because you can either use a 2-step 0 times, or 1 time, or 2 times, and that's it. So that's 1, 2, 3, 4, 5, 6, 7, 8 ways. So C5 is equal to 8. Now, hopefully you're looking for a pattern here, and maybe you've already seen it. If you're in the habit of teaching Fibonacci Sequence in your school, then you've definitely seen this before. But it suggests to us that this is a Fibonacci sequence, which is a recursive sequence where you can get the next term by adding the 2 previous terms. Like 8 is equal to 5 plus 3. 5 is equal to 3 plus 2. 3 is equal to 2 plus 1. And this would suggest to us that C6, right, the number of ways of going up the 6-step staircase, would be equal to C5 plus C4. In other words, hopefully, if this is correct, if this is a Fibonacci sequence, then the number of ways is just going to be 8 plus 5, or 13. But we can't just assume that this Fibonacci sequence is going to continue in this way unless we really understand why it's happening, right? So our claim, or our hope anyway, is that the number of ways to go up an n-step staircase, let's say, call it Cn, is the number of ways to go up n stairs, can be found by adding the number of ways of going up an n-1 staircase, so Cn-1, plus the number of ways of going up an n-2 step staircase, Cn-2. Why would that be? Well, maybe we can try to use what we have so far as a way of helping us understand where this is coming from, right? So, for example, we're trying to show that we can get these 13 ways of going up 6 stairs using the 8 ways from the case above plus the 5 ways from the case above that. So let's actually try to generate all these ways of going up the staircase using these 8 ways of going up 5 stairs and then using these 5 ways of going up 4 stairs, right? That's the idea with a Fibonacci sequence, is we can build up the next case using the 2 prior cases. Well, each one of these ways here in this box only gets us up 5 stairs, and we're trying to get up to 6 stairs. So we need to go up 1 more stair in order to turn a way of going up 5 stairs into 6 stairs, right? Into a C5 case, into a C6 case. But that's easy enough to do. If we just stick an extra 1 at the end, suddenly we've generated, stick a 1 at the end, and now we have a way of going up 6 stairs. Okay? It's not going to be all the ways of going up 6 stairs, right? Because so far all I've listed is the ways of going up 6 stairs that end in a 1. I don't have any ways of going up 6 stairs that end in a 2. But that's where this case comes in. Because up here in the C4 case, we had 5 different ways of going up 4 steps. So if I want to generate a way of getting up 6 steps, I need to go up 2 more steps. Now I've already listed the ones that end in 1, but I haven't listed the ones that end in 2. And conveniently, if I stick a 2 at the end of all of these, I've generated 5 new ways of going up a 6-step staircase. This is going to give you every possible way of going up 6 stairs, because if you're going up 6 stairs, then you either need to first go up 4 stairs and then jump up the last 2 stairs together, like in this case, or you need to first go up 5 stairs and then just take that one single last step, like in this case. So this gives us every possible way, and we can use this general argument to explain why Cn is equal to Cn-1 plus Cn-2, right? So make a little space here to generate all the ways of climbing n stairs. Well, there's 2 things that could happen. You could either, case 1, you could climb n-2 stairs and then take the last 2 steps at once, right? That's sort of like this case here where you just stick a 2 at the end. And we know that there are C sub n-2 ways to do this. Or you could climb n-1 stairs and take the last step as just 1 step. And we know that there's C sub n-1 ways to do this. We can add these together because they are disjoint, right? All of these ways of going up the stairs end in a 1 and all of these end in a 2, so we know that there's no overlap between them. And so by the addition principle, we get that Cn is equal to Cn-1 plus Cn-2. Great. Now that doesn't completely answer the question because we also wanted to do, well, we really wanted to figure out how many ways to climb up 12 stairs. But if we know how to continue this sequence, right, we can just sort of keep going here using the previous terms. So for the 7th term, we would add 13 plus 8, which is 21. For the 8th case, we would add 21 plus 13, which is 34. And going on in this process, we'd get 55, 89, what would this next one be? 144. And finally, for the 12 staircase, there's going to be 233 ways. Now, notice we had to build up the whole table all the way up to here in order to get to that 233. We didn't actually come up with a nice closed formula where we plugged in the number of stairs and it spit out the number of ways to climb it, but we'll come back to closed formulas in a little bit. Now number 2, once we've tried this, hopefully is a little bit easier now. So let's break down number 2 into smaller cases. So for number 2, you have 12 doors in a row. You can paint each door either blue or green, but you cannot have 2 green doors next to each other. So let's look at some smaller cases and work our way up. If our hallway had only 1 door or 2 doors or 3, this is an easier problem. All right, if your hallway had 1 door, then you could paint that door blue or you could paint it green. Those are your only options, so there's 2 ways. If your hallway had 2 doors, okay, now we can paint them in any way we want, provided there's no 2 green doors together. So you could paint them blue, 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 green, green, blue. The only thing you can't do is green, green, right? Green doors can't be next to each other. So there's 3 ways to paint with only 2 doors. If you had 3 doors in a row, again, anything's allowed as long as you don't have 2 greens together. So we just start listing them all. Blue, 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 green, blue, green, blue, green, blue, blue, green, blue, green. But there's no other way that we could use 2 green doors, right? There has to be a blue in between them. So we couldn't do, for instance, green, green, blue, or blue, green, green, or something like this. So there's only 5 options here. And for the 4 case, let's just list out the 4 case and then hopefully go from there. If we have 4 doors, they could all be blue. Or you could do blue, 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 green, blue, blue, green, blue, blue, green, blue, blue, or green, blue, blue, blue. So this is a way of using all blue or using 1 green. If we were to use 2 green doors, we'd have to keep them separate. So you could have green, blue, blue, green, or you could have green, blue, green, blue, or you could have blue, green, blue, green. But those are the only options because they have to be separated by a blue door and you couldn't have 3 green doors, otherwise there would necessarily be 2 together. So in total we have 1, 2, 3, 4, 5, 6, 7, 8, and we're starting to see that this is the same pattern we got in the last one, which suggests to us that for 5 doors you would have 8 plus 5 or 13, and then 21, all the way down, and we could continue in the same way. Now the sequence has been shifted just a little because in the last one the number of ways to go up 1 staircase was 1. So this one's starting at 2 rather than starting at 1. So it's just shifted a little bit. But the pattern itself is the same. And so once again, if let's say Pn represents the number of ways of painting n doors, it looks like Pn is going to be equal to P sub n minus 1 plus P sub n minus 2. And the question is why? We can only assume that this pattern continues if we can explain why it's happening in the first place. So let's try, just like we did in the last case, let's try to generate all 13 ways of painting 5 doors in a hallway using the 8 that we used in the 4 case and the 5 from the 3 case. So how can we use these 13 different ways of painting a hallway with either 3 or 4 doors to generate all the different ways for 5 doors? Well, let's think about this 4 case. We need to add a 5th door to each one of these sequences. And the question is, we want to do it in some way that's organized, that we can replicate. And so can we just add a green at the end of any of these? We can't, right? You could add a green to the end of this one or this one or this one, but you couldn't add a green to the end of, say, this one, because then I would generate 2 greens together, which is not allowed. So what I'm going to do is look at each one of these and stick a blue at the end. Because you can always put a blue door next to any other door. It's not going to break any rules because blue doors can be together, blue doors can be next to be green. Either way is fine. So we're going to just stick a blue door at the end of the 4-door hallway. So this is going to generate all of the 5-door hallways that end in B. But we're missing all of the 5-door hallways that end in G. Aha! Well, just go back to the 3 case And this time at the end we can stick a blue, and then a green. Now the reason we're putting a blue and a green at the end is because we need to add 2 doors to the end of it, but I can't put GG because GG is gonna, we can't have 2 green doors next to each other. And so I'm gonna put blue green at the end, and that's gonna give me all of my 5-door hallways that end in G. So this is all of the hallways that end in B, this is all the hallways that end in G. And just like before, we can justify this by saying to generate all the ways of painting n doors, you can take the p sub n minus ways of painting n minus 1 doors and add a blue door at the end. Or you can take the p sub n minus 2 ways of painting n minus 2 doors and add a blue, then a green door at the end. Okay, so once again, we've justified why this is a Fibonacci sequence, why we can add the previous 2 terms to get the next term, and this is going to allow us to get us all the way up to 12 doors. Right, I'm not going to do the whole thing, but it'd be, right, we'd do 34, then 55, then 89, and keep going until you got up to 12. And once again, we still haven't figured out a nice closed formula where we can describe how many doors there are in terms of, or how many ways to paint it in terms of the number of doors, but we can come back to that later. Now the last problem, I won't go through the whole thing, but I can at least get you started. We're building a brick wall with 2 by 1 bricks. How many ways can you build a 2 by 12 wall? So as an example, if the length of the wall is just 1 foot, then you have to put your brick going upright, so there's just one way. But if the length of your wall was 2 feet, you could put 2 upright bricks together, or you could put 2 horizontal bricks together, so there's 2 ways. In the 3 case, we could either do 3 vertical bricks, or we could do 2 horizontal followed by a vertical, or we could do a vertical followed by 2 horizontal. So this is going to be 3 ways. For 4, we could do 4 vertical, or 2 horizontal and a vertical, and another vertical, or vertical, horizontal, horizontal, vertical. This is getting tiresome. Or let's see, we could do vertical, vertical, horizontal, horizontal, or finally we could do horizontal, 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 horizontal. All right, so these are my 5 different ways of building a 2 by 4 wall. And you can probably see where this is going. There's going to be 8 ways to build a 2 by 5 wall. And just like before, we need to justify this in some way using the 2 prior cases. So how do we build up these 8 different walls using the 5 walls from the case before and then the 3 walls from the case before that? Well, we need to add 1 extra foot of length to each one of these walls. So we'll just put 1 vertical one at the end of each of these. Add a vertical brick to the end of the 2 by 4 walls and you'll get a 2 by 5 wall. Or we can go back 2 steps above and add 2 horizontal bricks to the end of these. Right, so add 2 horizontal bricks. Okay, and so that's going to give you all of your different ways to generate a 2 by 5 wall. Now once again, you would want to justify if we call this number Bn, you would want to explain why bn is equal to b sub n minus 1 plus b sub n minus 2. And then you can use that to build up your sequence from there. So in the next video, we'll talk a little bit more about what we mean by a recursive sequence versus a closed formula for a sequence. And we'll see why this particular problem is especially hard to find a closed formula for.